Euclid's Elements, Book 1, Prop 48. If in a triangle, the square on one of the sides equals the squares on the other two sides, then the other two sides must contain a right angle. This is the converse of Prop 47, right? Prop 47, we start with a right triangle and we show that the hypotenuse, the square on the hypotenuse is equal to the square on the legs. Here we're starting with the square on one of the sides is equal to the other two, and from that we're going to conclude that we have a right angle. So here's our given. We know, so let's start with ABC. So in triangle ABC, let the square on CB be equal to the square on the other two sides. So the square on AB plus the square on AC. From this, we will prove that the angle contained by those other two sides, namely angle BAC, will be a right angle. So that's what we're going to prove, that this is a right angle. So let's keep track of what we're going to do and why. The first thing we're going to do is, on this line at a point, we can construct a line perpendicular to a given line. So we're going to make AD perpendicular to AC. We can do that with Prop 11. And we can extend this as far as we wish, and from this longer line we can cut off a piece equal to a given line. So we can make AD equal to AB. And this is just Prop 3. So now let's shorten this here and make this the same. So here we go. So now we have AD equal to AB. Let's connect CD. And we know that these are equal to each other. So if AD is equal to AB, then we know that if we make a square on both of these, then those squares will likewise be equal to each other. So if the sides are equal, then the squares we build out, those equal sides must themselves be equal. So we can say square AD must equal square AB. Now at this point, we don't know or care if this line is in line with this line. It might be, it might not be. At the end of this, we'll be able to show that it is, but it doesn't have to be for this proof to work. So we know that these two squares are equal. So let's add equals to both of these. Let's add the square on CA to both sides. And what do we get? Well, here we have a right triangle, and if we add the square on this side plus the square on this side, CA, what do we know we're going to get? We know we're going to get the square on the hypotenuse, the square on DC, the side opposite or subtending the right angle. So these two squares added together give us the square on DC. But look at this. This square plus this square, these two give us the square on CB. This is Prop 47 that tells us this, and our givens tell us this, which means the square on DC must equal the square on CB. Well, if the squares are equal, then just like we built this line up into a square, we can unbuild this square into a line, and we can just say, well, then the ordinary line DC must be equal to the ordinary line CD. Therefore, this must be equal to this. And now notice we also have another line in common. We have line AC. So we have side 1, side 2, side 3. That's side, side, side. And so that lets us use Prop 8, the side, side, side theorem, to prove that the angle contained by any two sides must be equal. So if we look at the angle contained by sides 1 and 3, it must be equal to the angle over here contained by sides 1 and 3. And since this is a right angle, therefore this must be a right angle. Therefore, according to Prop 8, since all the sides are equal, this angle BAC, must equal angle DAC. But DAC is a right angle, therefore BAC is a right angle. And that's what we're trying to prove. Now from that, we could then show through Prop 14 that this line is in line, but we didn't need it for that point. So since we have proven what we're supposed to prove, namely that if the square on one of the sides equals the square on the other two sides, those two other sides must contain a right angle. Since we've done that, we conclude QED.